we're going to look at the concepts of energy and work. Okay, this is all working towards our next couple chapters, which deals with energy and momentum. But in this particular chapter, we're going to focus on energy, right? Energy and momentum are the next 2 consecutive chapters, but this chapter itself is looking at energy and work, okay? When we talk about the concepts of energy and momentum, we think about the term conserved or conservation. Okay, so when I say the law of conservation of energy, does that ring any bells, or does that sound familiar? The law of conservation of energy. Okay, what about the law of conservation of mass? Mass cannot be created or destroyed. Have you heard that before? Mass cannot be created or destroyed. Okay, it's the same thing works for energy. So when we say they are conserved, that means that they are neither created or destroyed. Okay? So what that means is that in the universe, there is a finite amount of energy, right? There is a set amount of energy that's contained within the universe. And that energy is just constantly changing forms, right? From the sun, the wind, to electrical, to light, to heat, to chemical within our bodies, right? All of these versions of energy are just transformed from one to another, right? If we go all the way down like the food chain, right? It starts with the sun, then the plants, then the animals, then the humans, right? And all of this energy that we consume, right, has to come from somewhere and then recycles to somewhere else, right? It's all part of that cycle. But the actual amount of energy in the universe is conserved. It's not coming from nowhere, and it's not going to nowhere. It's just changing forms. Okay, the same is true for momentum, but we'll get into that in our next real chapter. But that's what it means to be conserved. When we say the conservation of energy or conservation of mass, that means that it's not created or destroyed, right? It just changes forms. Okay, so we're going to take a look at energy and work, and we're going to start with work. Okay, what is work? When we think about ourselves doing work, we think about exerting effort, right? Running, playing a sport, lifting something. I don't know. All of these things that we exert effort for, we consider to be work. But in physics, work takes on a different definition. Okay, the definition of work in physics has to deal with force and displacement. Okay, so it says that work is the product of the magnitude of the displacement. Okay, so the product of the displacement times the component of the force that is parallel to the displacement. Okay, so work is essentially force times displacement. Okay, the force of an object, the force that it is exerted on an object that causes it to move, then that means work has been done. Okay, so what I want you to put in here with this equation should go on your equation sheet. I'd probably put it under the category of energy and work, right, if you want to make a category for it. But this is the equation for work. And with this, I'm going to go ahead and put a parallel in for that force, right? We're not talking about, we're going to look at parallel force. So it's not 11 there. That means parallel, okay? So when we say force parallel, we're talking about parallel to the displacement, okay? Which means that if my displacement is horizontal, I only want the horizontal component of my force, okay? I don't want the force that's at an angle. I don't want the vertical component. If my displacement is horizontal, I'm only concerned with the horizontal force, okay? So you can essentially put it like that, force parallel times displacement, okay? All right, so here's just another explanation of force parallel, okay? Parallel is the component of the constant force that is parallel to the displacement. So in this particular example, right, in this case, displacement is going to the right or east, or it is horizontal, right? See how our displacement is here is given right this. Our displacement is to the right, okay? But essentially it is horizontal. But my force is being applied at an angle like this, right? I'm dragging the object. So I don't want this force. I want this. I want the parallel component of my force. So I would take cosine of that force to be able to get the horizontal component. Okay, does that kind of make sense? I want the force that is just parallel. So if my displacement were vertical, right, if my object was being lifted, I would want the y component of the force. Okay, but it's not being lifted here. It's just dragged, but that's what would happen if it were lifted. Okay? So if I pushed a loaded grocery cart a distance of 50 meters by exerting a horizontal force of 30 newtons on the cart, how much work would be done on the cart? Okay, if I were going to exert, here's my cart. I'm going to exert a force of 30 newtons, but my object moves 50 meters. Okay, so if I was going to solve for work, I want to take force times displacement. Are my displacement and my force, are they parallel to one another here? Yeah, because it says my force, I'm exerting a horizontal force. And where did my grocery cart go? Does my grocery cart go in the air? No. All right, it goes horizontal too. So I would take work equals force times displacement, okay? And I get 1,500. Okay, and the units here start out as Newton and meters. So my units would be Newton times meters. Okay. However, this unit right here is actually given a nickname or a new name, which is actually joules. Okay, so really we're going to measure work in what's called a joule. Okay, joule is the universal unit for work and energy both. Okay, so it's just given in a capital J. Okay, the unit for work is joules. Okay, and so a joule is equal to 1 Newton times meter. 1 Newton times 1 meter. Okay. All right, I want you to think about these questions. Can a force be exerted on an object, yet no work be done? Okay, think about that. And then think about what work is done on an object that's carried as you walk at constant velocity. I want you to think about those two questions. I'm going to give you about a minute or two. Think about it, and then we're going to see what we think the answers are to these questions, right? Can a force be exerted on an object, yet no work be done? And then what work is done on an object that you carry and you walk? Okay, so think about those two. Can a force be exerted on an object, yet no work be done? What do we think? Yes or no? Yeah? Okay, can you think of an example for that?
Pushing up heavy stuff.
Yeah, very good. Okay, perfect. If I push on this wall, right, no matter how hard I push, what's never going to happen? It's not going to move, right? It's not going to move. There's no way I can push on this wall just with me and cause that wall to move, right? I can apply a force, but there is no displacement that's happening. And if there's no displacement, that means no work has been done. So I can try to lift this crazy heavy table, right? And it feels like I'm working really hard, but it doesn't move, right? So no work has been done, okay? Good. What work is done on an object that's carried as you walk at constant velocity? Okay, is there any work done or not?
Would it be vertical?
Yeah, okay, good. Okay, here's what I want you to look at. From here to here, there's work that's being done, right? This lift, work's being done because the force that I'm exerting to hold it upright is vertical. And it moved in the vertical direction. But when I start walking, right, the force I'm exerting on this object to hold it upright is vertical. But when I walk, what's the displacement? Horizontal. Which means technically no work is being done on this book right now. Okay, on this object right now.
Well, aren't you like working against gravity?
So I am, but it's not moving vertically. Right? So the work is done when I lift the book, right? And then when I start moving, no work is done on the object. I'm doing work on myself to make myself move, right? But on the object itself, right, work is done here, but is no longer done here, right? Because there's nothing that's pushing it that way. It's just being carried, right? The force I'm exerting is vertical, but it's not moving vertically anymore. Does that kind of make sense? So carrying an object is often no work. Right? It feels like you're working hard maybe, but the object itself is having no work done on it. Okay? I think work itself I think it's kind of a tricky concept because it's kind of counterintuitive to what we think about traditional work. Okay? So when we're looking at work, we want to remember two things. We have to specify if we're talking about work being done by an object or on an object. Okay? So in our last example with carrying the book, right? No work was being done while it was being carried, right, on the object. I myself was exerting a force and moving a displacement, right, for me to be able to walk. But on the book was no work, okay? Second thing we have to specify is that if we're talking about the work being done by a particular force, or if we're talking about work being done overall, right, the net work. So we have the ability to calculate the work done by gravity, the work done by an applied force, the work done by friction, the work done by, air resistance, right? Any forces that we know, we can calculate the work done by that force. We can also calculate the net work of our system, right? The net of our system, and do it that way, okay? All right, let's try a practice problem here. I actually want to skip one slide, and we're going to try this determine the work on a hiker must do. I want to do this one first, and then we'll go back to the other one, okay? So this one says, determine the work that a hiker must do, right? So I'm only finding the work of the hiker, not the net work. I'm going to show you two ways to go about these problems, and then you can decide which one works best for you. I'm going to show you first where we break it down and solve for work by an individual force. And then the next problem, we'll find the net, and then we'll solve it from there, okay? So there's two ways you can go about the problems. I'm going to let you choose which is best for you. But I want to find the work done by the hiker to carry a 15-kilogram backpack up a hill at a height of 10 meters, okay? So I drew the free body diagram over here of my object. Here's my, my backpack, whatever, and then the force applied by the hiker and the force applied by gravity. I want you to just envision the backpack on the hiker's back. Is the backpack itself, is it accelerating? No, right? It's just resting on his shoulders, right? So for all intents and purposes, our backpack is just resting, right? It's sitting on his shoulders. He's having to exert a force upward to keep it from falling due to gravity, right? But he's exerting that force. So in this case, if the backpack is just resting, what do we know about these two forces? If it's not accelerating vertically, what has to be true about those two forces? They're equal, right? So they have to be equal to one another, okay? So that means if I'm trying to solve for the force of the hiker and I know it's equal to the force of gravity, I can just calculate the force of gravity, right? And then it would be equal to the hiking force, okay? So how do I calculate the force of gravity? Fg equals mass times 9.8, right? The way I always calculate the force of gravity, mass times gravity. Okay, so I'm going to come over here and I'll say the backpack has a mass of 15 times 9.8 equals the force of the hiker. So 15 times 9.8 gives me 147 newtons, right? Do you remember the unit for force? Any type of force has a unit of newtons. All right, so that's my force, but I want to find the work that's being done, okay? So if my object is moving up a hill, right? It's going up a hill 10 meters. The height of the hill is 10 meters. I do not care how the object is displaced from the bottom to the top. It could have rode an escalator up for all I care, right? Work is not a path function, okay? Work is not concerned with how we get from point A to point B, okay? It makes no difference whether he went 2 meters and stopped, then he took an escalator, whether somebody flew him to the top of the hill. It makes no difference how he got there, right? All that work is concerned with is bottom to top, right? Start to finish. It makes no difference how he got there. He could have wound his way up to the top. He could have sprinted up to the top. It does not matter, okay? The amount of work that's done is the same. So when I calculate work, I take force times displacement. And so since my vertical displacement here is 10 meters from my hill, I'm going to take my vertical force, 147, times my 10 meters, and I get 1470 joules. Okay, so that is the work done by the hiker. Okay, the work that is done by the hiker on that backpack. Any questions with that? Right, we isolated one force and we're able to calculate that work because the force was applied over the whole distance. Okay. Second one says, find the work done by just gravity. Okay, the work done by just gravity. So what did we know about the force of the hiker and the force of gravity? They were equal to each other. So we already know the force of gravity is 147 newtons, right? I already calculated that in my last part of my question. Is gravity working the whole 10 meters? Yeah, because gravity never stops working, right? So that means the work done by gravity is still force times displacement. 1470 joules, right? They're the same. Okay, this one is pointing in the downward direction because gravity is pulling us downward. So if I'm going to calculate the net work done on my system, on my backpack, what do we think it's going to be? Right? If I have 1470 joules of work upward and 1470 joules of work downward, what's my overall net work going to be? 0 joules. Okay, and that's it. Right? So the work that each of those forces was doing just ends up canceling out, right? Because we said from the beginning, the backpack is essentially at rest on that person's back, right? So essentially no work was done on the backpack. No net work, I should say that. No net work is done on the backpack. Okay? So that's one way you can go about it, right? If my overall goal is to find the net work, I can solve for individual work and then bring it together. But I'm going to show you the alternative method of how to do that, and probably my preferred method. Okay, so let's go back to that question here that says a 50 kilogram crate. Okay, a 50 kilogram crate is pulled 40 meters along a horizontal floor by a constant force of exerted by a person at an angle of 37 degrees. The floor exerts a frictional force of 50 newtons. Determine the work done on the crate. Okay, so I drew my free body diagram here, right? Do you remember our free body diagrams? Does that look familiar? Okay, we've got our forces here. What do I call this force here that's pulling us downward? Force of gravity. Good. What about the one that's opposing or from the surface? The normal force. Good. And then this would be the frictional force, and we would call this F applied, right? Because I'm applying that force. This one equals 100, and my frictional force equals 50 newtons. Okay, so let's determine now. It says it's pulled 40 meters along a horizontal floor. So my object moves a total of 40 meters in the horizontal direction. So when I'm looking at this diagram, am I going to be concerned with the vertical forces or the horizontal forces? Horizontal, right? Because my displacement is horizontal. So I need to concern myself with the horizontal forces, which means I am going to have to solve for F applied X, right? I need to know what is that force so I can account for all of my horizontal forces, okay? So to find F applied X, I'm going to take 100. Am I going to use sine or cosine? I'm going to use cosine, right? Because this is adjacent and the hypotenuse, right? So katoa, okay? So I'm going to use 100 times cosine of 37 degrees. And I get about 79.9 newtons. Okay, if your calculator doesn't come out with 79.9, if you plug it in just like that, make sure you let me know because your calculator might be in radians, right? We want it to be in degrees for this, especially since we're calculating with sine, cosine, and tangent. Okay, so that is my applied force is 79.9. So now my overall goal is to find the net work, the overall work. So what I want to go ahead and do is actually just solve for what's my net horizontal force. Okay, and I would say F net equals F applied X minus force of friction, right? Positive forces minus negative forces. Do you remember this part in our chapter on forces that we did all this? Right? We took our net force and we took our positive forces minus our negative forces, right? We're doing the same thing here. We're just calculating the net horizontal force. So that would mean F net would be equal to 79.9 minus 50, which is 29.9 newtons. Okay, so that's my net force, but now I need to go solve my work, right? Work is equal to force times displacement. And so that gives me a value of 1,196 joules. Okay, alternatively, I could have found the work done by the applied force. Take that times 40. The work done by friction, take that times 40 and then subtract the 2, right? But it makes a little less math for myself when I find the net force. Then I take that times my displacement. Energy is essentially, I think, the most important concept in science, right? Every single science is built around energy. It's a concept you talk about in every chemistry class, right? Energy comes in tons and tons of forms. In biology, you focus on the energy transferred in the food chain. In chemistry, you talk about energy that happens in chemical reactions. In physics, we go big picture, right? What's the energy stored in a system, right? But essentially, our sciences are built around energy and energy transformation. So it's a big, big, big topic. So we're going to cover two kind of main categories of energy, okay? The type that we're going to focus on is called translational, kinetic, and potential energy. And so, do you remember in geometry what it's called if you have a graph and it translates? It kind of just means slides, right? Is that what that means in geometry? Am I saying that right? It's not flipping, it's not rotating, it just slides. Is that the word for that or no? You don't know. Okay, that's fine. I think it is. We'll see. But we're essentially talking about motion that's just moving from point A to point B pretty simply. Not in spinning, not in rotating, things like that. So translational, kinetic, and potential energy. So this is the main big category that we're going to talk about, kinetic and potential energy. Other types of energy would be electrical, thermal, nuclear, right? Those are not types of energy we're going to focus on. We're going to focus on our mechanical type of energy, okay? So energy's most basic definition is the ability of an object to do work, okay? We have to know what work is first to be able to understand the definition, but energy is the ability of an object to do work. So that means, does my object have enough energy to apply a force to something and make it move? Right? Can my object apply a force and make it move? Right? Those are the types of things we're looking at here. Okay, so the first main category of energy is called kinetic energy. Do you know what the prefix kina means? Right? We studied kinematics for most of the first semester. What do you think kina means? Or kinesthetic? Kina means motion, right? That prefix kin means motion. And so kinetic energy is the energy of an object that is in motion. Energy of an object in motion. And here is our equation for kinetic energy. So you can go ahead and get that copied down onto your equation sheet, right? Kinetic energy equals 1/2 mv squared. So what do you think the m stands for here? Any idea? Mass. And that needs to be measured in kilograms. And then V has to stand for velocity, which needs to be measured in meters per second. Kinetic energy being transferable. It says when one object exerts a force on another and the second object is moved to a certain distance, then work has been done. But I want you to think about the transfer of kinetic energy in terms of playing pool. Right? Playing pool or billiards, right? You have the cue ball, you hit the cue ball, and then what happens when it hits another ball? The other ball moves, right? So first thing happens, I'm transferring energy from my pool cue into the cue ball, right? It puts that ball into motion. In a perfect kinetic energy transfer, what would happen is the cue ball is coming, it hits the other ball, right? What's happened is this ball at rest, right? First ball's at rest, cue ball's coming. What would happen is that this cue ball would transfer all of its energy into the other ball. The other ball would start moving and this one would come to a stop. That would be a perfect kinetic energy transfer, right? It's just like that. It's like those desk decorations. You see those little Newton's cradles, right? Where there's several little balls on the string and one hits it and the other one flies up, the other one flies up, right? That is a perfect transfer of kinetic energy because all of the energy from one object is transferred and given to the other. and it will move in exactly the same situation as the previous one, right? A perfect kinetic energy transfer is when all of the energy is transferred from one to the other and they switch what they were doing, right? If one was at rest and two hit it, then now two's at rest and one is moving. Okay, that's what it would look like. Okay, so here is our equation for kinetic energy. We see kinetic energy and work having a big connection, right? When an object is displaced, right, it's put into motion, then work has been done, okay? And so we're going to be able to connect work and kinetic energy here in just a second, okay? Kinetic energy is measured in joules, just like work is. So the unit for kinetic energy is joules, all right? We have a way to connect work done and energy with this equation, okay? Net work is equal to the change in kinetic energy, right? We know this symbol right here stands for what? Change in, or delta, right? It means delta, and so it means final minus initial. So the net work being done on an object is equal to kinetic energy final minus kinetic energy initial. And so essentially, this equation gets spread out even more. Net work is equal to 1/2 mvf squared minus 1/2 mvi squared, right? Do you see what all I did there is plug in the equations for kinetic energy into that? So I would say some combination of those equations need to go on your equation sheet. If you want to do just the bottom one, if you want to do just the top one, all three, I don't care. But you need to know that connection between the work and the kinetic energy. Okay? It's really, really important that it's net work, not just the work done by friction or the work done by the applied. It's the overall. Okay? So go ahead and put that on your equation. It says 145 gram baseball is thrown with a speed of 25 meters per second. What is its kinetic energy? So that's question one. How much work was done on the ball to make it reach this speed if it started from rest? Okay, so we're going to first start identifying what variables we have, right? 145 gram has to go with what? Mass or velocity? Has to go with mass. And do you see a red flag there? It's in grams. It needs to be in kilograms. So we're going to divide by 1,000 to put it into kilograms, right? Which would become 0.145 kilograms. Okay. Second number was 25 meters per second. That has to be velocity. Okay. My first question says, what is its kinetic energy when it's moving at 25? Okay. So all I'm going to do here is take that kinetic energy equation. Kinetic energy equals 1/2 m. V squared. 1/2 mv squared. Okay, so 0.5 times 0.145. And I get a value, I don't know, what'd you guys get? I got about 45.3 joules. Is that similar to what you had? Okay. 1/2 times m times v squared. So that answers our first question. What's the kinetic energy? How much work was done on the ball to make it reach that speed if it started from rest? So we know that work is equal to kinetic energy final minus kinetic energy initial. Okay? Well, what do we know about our kinetic energy if it started from rest? What was our initial kinetic energy? It was just 0, right? So if I'm using my work and my kinetic energy final is 45.3 and my kinetic energy is 0, my work is also equal to 45.3 joules. Okay? If I would have had a different starting speed, I would have had to plug that in, right? I would have had to do another 1/2 mv squared, but I didn't. My velocity was 0, which means that my kinetic energy was 0, right? Because anything times 0 is 0. How much work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Okay. So how much work is required? So we know that work is equal to force times displacement. Does that work for this Does that work to solve here? No, so I can't use that one. I also know that work is equal to change in kinetic energy. Does that seem more likely to help me get to my final answer? Yeah, so I'm going to have to use that equation, right? My work is equal to kinetic energy final minus kinetic energy initial. Now, you could solve kinetic energy separately and then plug it in, but for me, it makes the most sense to just say work is equal to 1/2 mvf squared minus 1/2 mvi squared, right? I just like to do it in one equation if I can, okay? So now I'm going to put my numbers in here. Work is equal to 1/2 times 1,000 times velocity final, 30 squared, minus 1/2 1,000 times 20 squared, right? It's really important that we do the order of operations correctly here. Sometimes we'll want to factor that out and then just do 30 minus 20 and square that, but that's not the same. Okay, so we need to go ahead and make sure we do that order of operations correctly.